Figure 1 shows a sketch of the curve C1 with the equation f of x equals x over 3 plus 12 over x for x not equal to 0. We're told that x equals 0 and y equals x over 3 are asymptotes to C1, and the latter's been drawn as a dashed line. And then the point A on C1 is a minimum, and the point B on C1 is a maximum. Let's find these coordinates. So they are stationary points, and therefore we can find out df by dx. First of all, just write it as a third x plus 12 to the x minus 1. So df by dx equals a third. Then it will be minus 12 to the x minus 2, or minus 12 over x squared. And it's going to equal 0 for stationary points. We can rearrange this. So 12 over x squared will equal a third, which means we can cross multiply. X squared is going to equal 36. So x is plus or minus 6. X equals 6 is going to be the minimum, because we can see it from the graph. So f of x will then equal 6 over 3, or 2, plus 12 over 6, which is also 2, so 4. And therefore a is 6, 4. X equals minus 6, very similar, but it's going to be minus 4, which gives b minus 6 minus 4. All right, nice start to this question. We're then told there's a normal to C1 which doesn't intersect a second time, that has equation x equals k, so a vertical line where k is greater than 0. Write down the value of k. Note there's only one mark. And the only way we're going to get a normal that is vertical is if we have a tangent that's horizontal. And that's going to correspond with the stationary point that we found before. So it's got to be a normal that goes through A. And remember, we've just found the coordinate of A. It was 6, 4, and therefore x is going to equal 6. So that's going to be our value of k. K equals 6. We're told that there's another point, P, alpha, beta, but now, and alpha is greater than 0, but now alpha is not equal to k, so it's not the same line, where we also do not intersect C1 a second time. We're asked to find the value of alpha, leaving our answer in simplified surd form. Right, this is there's a lot more to this one, as you can see in the marks. So if we draw, say, a tangent here and then the normal, we intersect, but we are going to intersect again down here. So that's no good. And that's going to kind of be the theme throughout. Well, I could draw one over here, but then, well, actually, maybe this one wouldn't intersect. If we slightly change it, then we can see it's going to come down and hit here. So the only way that it's not going to intersect a second time, actually, is if the normal has the same gradient as this asymptote, i.e. a third. As soon as it's something else, if it's slightly greater than a third, then it's going to come down and eventually it's going to hit the curve here. And then if it's less than a third, it's going to sort of come across however we have it, and it's going to hit again over here. So the one place where it will just intersect once is when we get the normal gradient equal to a third. And that means the tangent gradient will be minus 3. So this is part C, require normal gradient equals a third. Applies. Might as well work in terms of the tangent because we've got a dy by dx. So remember, we worked out dy by dx. it was, where was it? It was a third minus 12 over x squared. So therefore, a third minus 12 over alpha squared is going to equal minus 3. Minus a third from both sides. This gives minus 12 over alpha squared is minus 9 over 3 minus a third. That gives minus 10 over 3. I can times through by minus 1 to make them both positive, get rid of these two. And then alpha squared, if I times through and then times through by 3 over 10, will be 12 times 3 over 10, which gives, what can I do here? 36, okay, 36 over 10. Let me leave it like that because 36 is a square number. And therefore alpha will be 6 over root 10. I've square rooted the whole thing. I can square root 36, square root the 10. And remember, we know that alpha is positive, so we can ignore the negative solution. There will be another solution, but it will be for at the bottom of the curve. So in the same sort of position here, I guess. Wait, we're going to need to get that there will be another place. Yeah, maybe a little bit like that, where that would correspond with minus 6 over root 10. But that is our answer in simplified surd form. We could separate it and write it as root 2 root 5, but I think that is fair enough. Let's define the equation of the normal. So we now know that alpha is 6 over root 10. So I can put that back into the original function. So I'm a bit all over the place. I'm just trying to not, have the question here as well. So when x is 6 over root 10, y is going to equal 6 over root 10 divided by 3 plus 12 over 6 over root 10. Did not leave enough space, did I? So I can actually divide the 6. This is the same as times in by 1 over 3, so this just becomes 2 over root 10. And over here, it's the same as doing 12 times root 10 over 6, which becomes 2 root 10. I can rationalize the denominator here, so I get 2 root 10 over 10 plus 2 root 10, which I could write as 20 root 10 over 10, which gives 22 root 10 over 10, or 11 over 5 root 10. And that's actually my value of beta. And to be fair, maybe I should have rewritten alpha as 6 root 10 over 10, or 3 root 5 over 10. Yeah, okay. Kind of prefer that, to be fair. So for the normal, we have the gradient. Remember, it's a third. So we can write down y minus y1 equals m times x minus x1. So in this case, y minus 3 over 5 root 10. Wait, that's my x value. Sorry. 11 over 5 root 10 equals a third x minus 3 over 5 root 10. And let's simplify this. So y will equal a third x minus a fifth root 10 plus 11 fifths root 10. This becomes 10 over 5 root 10, or simply 2 root 10. So it simplifies really nicely. Good. Given that the curve C2 has equation the modulus of f of x, and we're asked to sketch it, stating the coordinates of any turning points and the equations of any asymptotes. All right, now there's my original curve. So we're definitely going to get the same asymptote as before. It's a third, so let me just try and show that the gradient's less than 1, something like that. And then I've got the curve coming down and then tending towards this asymptote. But then on the left, we get a reflection in the x-axis. And this part of the asymptote is also going to be reflected. So I'm going to get a second asymptote. It's going to be minus a third x. And then the curve will end up looking a bit like this. It's meant to be a reflection. It's not too bad. I think it's good enough. Actually, I'm not happy with it. Let's do it again because it should be tending towards the asymptote. Okay, so something like that. Now we've got our two turning points. The first one is still 6, 4. That was the original A, stays the same. Before we had minus 6, minus 4. It's just going to become minus 6, 4. And I think that's everything we need. Turning points and the equations of the asymptotes. So y equals the modulus of f of x. One thing I just realized I've forgotten, actually I forgot it when I originally did it as well, is we also have this asymptote x equals 0. And I think it's probably best to just identify them. I just point some little arrows at them. And the others, other turning points, I'm just going to make that really clear. Okay, that's a bit better. Finally, we're told that the line with equation y equals mx plus 1 does not touch or intersect C1. So we've got this intercept here, and we're trying to find the set of possible values for the gradient. So we can see straight away that the gradient of 0 would work. We just get this horizontal line. And then there's going to be some sort of cutoff where it just glances off it or it just misses over there. And then the same over here. It might not look quite to scale. It's going to be the same, like there's going to be some symmetry going on. So these, I'm expecting to get the same value magnitude of each gradient, even though one will be negative and one will be positive. So we can see that from the graph. I'm just going to get rid of them because that kind of wrecks my answer to E, but I just wanted to demonstrate it. So what we can do is set mx plus 1 equal to, well, we could do the modulus of the function, but that's going to create a modulus equation. And like I said, there's symmetry in the problem. So I'm actually going to set it equal to the original function, which was x over 3 plus 12 over x. But I'm only looking at x being greater or equal to 0 here. Because as soon as it goes below 0, we've got this reflection now. I'll talk a bit more about it in a minute. And now we're going to try and find the possible values of m. So I can multiply through by 3x, which will give me 3mx squared plus 3x is equal to x squared plus 36. And this is a quadratic. Now, for there to be no points of intersection, it's going to be that the discriminant is less than 0. So let's get it in the form ax squared plus bx plus c equals 0. 3m minus 1 x squared plus 3x minus 36 equals 0 for no points of intersection. The discriminant, which is b squared minus 4ac, is going to be less than 0. And that means that 3 squared, or 9, minus 4 times 3m minus 1 times minus 36 will be less than 0. Can divide through by 9 because there's a common factor to make this 4. So 1 plus 16, because there's a minus 4 times minus 4 here, 3m minus 1 will be less than 0. So 1 plus 48m minus 16 is less than 0, which means 48m will be less than 15. I can divide through by 3, so 16m will be less than 5, and therefore m will be less than 5 over 16. So remember, this is only true for x is greater or equal to 0, and because I'm going to get into some difficulties, like for example, if I make it negative, then I'm actually, because I've now got the modulus function, I'm going to hit the function here. So I need to think about when x is going to be less than 0. And for that, if I follow through, I'm not going to do the calculations again, but I can see by symmetry that I need that m is going to be greater than minus 5 over 16, because there's this symmetry to the problem. And therefore, overall, for it to work throughout for our equation that's had the modulus applied to it, we've got the minus 5 over 16 is less than m, which is less than 5 over 16. So I'm just going to talk about this bit very quickly again. We looked at the discriminant and we found that m was greater than minus 5 over 16, but that only applies to the original function, whereas our actual function is the modulus of the original function. So we also have this bit at the top left. So you can't go having lots of negatives for your gradient because we'd actually hit the function. So we need to think about this other kind of set of values here, like I drew originally. And we said like by symmetry, I just need to flip the gradient around. So just like I've got m needing to be greater than minus 5 over 16 to avoid it, to avoid, oh, sorry, m is less than 5 over 16 to avoid it hitting this. We also need m to be greater than minus 5 over 16 to get it to hit this. So I've dealt with that kind of separately after I dealt with the original problem. I just need to take it into account, and that gives us our final inequality. Right, that was my second effort of explaining it. I hope that makes sense. Good question. Well done.